Hayward Group 16, Team Megahertz, and I'm Martin Chen.
I'm Brent John.
And I'm Kyle Boyne. Our project was the Ezra Rocket Technical Payload.
ESRA stands for Experimental Sounding Rocket Association. They have a competition held annually in Green Lake, Utah that allows students a chance to compete with each other at a technical and design level. That's
Okay, so this is our project overview, and over here on the TV screen is actually the board that I designed. So back here we have our GPS. Down in this corner we have all our analog sensors, thermocoupler for the exhaust temperature, and the external temperature chip. Moving on, over here we have I2C chips. We have barometer to measure our elevation. Accelerometer measures the acceleration of the rocket, and the gyro measures the tilt during flight. With the gyroscope, we have servo pins connector that our programmer programs to allow us to do stability control. Moving on, we have power supplies in the corner over here, which will provide us power to the board and the BeagleBone. And we also have some debugging LED lights for coding purposes.
So I'm going to talk about the microcontroller block. For this, we chose to use the BeagleBone Black, which uses a Texas Instrument chip. It's a Cortex ARM A8 processor. It can run up to 1 gigahertz. And what's special about this processor, it has multiple modes, so we can set each pin to be an I2C bus, a UART bus, GPIO. It has analog to digital, and PWM. This fits into our overall design because we have things like the altimeter that run on I2C, the accelerometer that runs on I2C, but also things like the GPS that run on UART. Over here we have the temperatures that run on analog to digital, and altitude that also runs on I2C, which is the gyroscope. By selecting, we use something called pin muxing to select the mode for each pin. Each pin can have up to 7 modes. Also, what's special about the BeagleBone Black is that from our power source, our power supply, we send 5 volts to the microcontroller. The microcontroller will step down to 3.3 volts, which all of our sensors use. This makes it convenient for power control and system delivery. And this is the end of the microcontroller block. I'm going to talk about the code block. So the code block interacts with the microcontroller, so it's basically input-output and interacts with all the sensors. So the basic design of the code was, since the microcontroller actually runs Angstrom Linux, which is just a distro of Linux, and so we can just SSH into that and program straight into it. So it makes it really easy to program. So basically the design is that we read the data, store the data, wait so many microseconds or seconds, and then repeat. All of our sensors between the accelerometer, gyroscope, temperature sensors were all pulled at 1 hertz. But we decided that it wasn't enough for the accelerometer because due to the initial launch of the rocket, that we might need to increase that. So the accelerometer actually pulls at 10 hertz, so 10 times per second, so that the propulsion team can either improve their design for next year by seeing the amount of G's they used or saw from that rocket flight. All the code was programmed in Python and runs on Linux. And that is the code block.
power supply block. If you look at our board, you can see it implemented here. We have a cap and inductor, cap and inductor in our chip. We also have our Schottky diode. And now we're going to show you the schematic, which is here. The chip we use is the AP 1509-50, which is a 5-volt step-down buck converter. It steps down 7.4 volts to 5 volts at a 1 amp load. The parts chosen were a combination of what the data sheet recommended and what we calculated. The layout itself was provided from the data sheet. The input cap and the Schottky diode were provided from the data sheet. The calculated values we came up with were for the inductor and then the output and the capacitor in the output. And the equations we used are down here on the page, right here. So we found the duty cycle, we found the ripple we wanted, we've picked the inductor and the output. And that's our power supply block. This is our GPS block. And as you can see, if you look at our board, this is our GPS here. Here is our connector for the external antenna. Here's our LED, which we'll talk about later. here is our GPS antenna. It's an external antenna we use on the board. Here's our schematic of the GPS. We use USART here in these two pins to talk to our microcontroller to get the location to and from the circuit. We have an LED that shows if we have a signal lock. If it doesn't have a signal lock, it'll blink every second. If it has a signal lock, it'll blink every 10 seconds. That way we know if we're getting a reading or not. Here's the port for the external antenna. And this is our basic layout of the circuit we used. We have a reset pin we used. We need to reset the GPS if we're having any problems with it. For the most part, the data we get from this, we could use on Google Maps, and we could see the trajectory of the launch. This is our GPS block.
Alright, so we're going to show a backup video of stability control. We don't have a mechanical built system ready yet, so we're just going to simulate the servos. So we're going to run basic code here. And we're going to tilt, here, come on the servos, Martin. Tilt the board, and you should see the servos turn very quickly, actually, to the off-center of the accelerometer. Like I said, we only have 2 right now, so we can't simulate all 4, but we will have 4.
Some helpful hints for seniors next year. Make sure you keep track of all your stuff. It's easy to lose things. We lost a few things. Make sure you try and purchase anything from one vendor. Makes it easier and help with that.
One thing about making PCB is you're paying people to actually remove copper, so keep as much copper on your PCB as much possible.
My hints are prototype early, because things do come awry and problems will arise. And keep your website up to date to keep yourself organized and your team organized, because that really does help.
Good luck.